honor for me to begin and present your PhD defense. So first of all, I would like to introduce, on a commencé, to introduce the jury member. Online, we have Nadège Meunier, who is professor at Grenoble, IPAG. Then, by this order, Magali Deleuil, professeur at Marseille, laboratoire d'astrophysique de Marseille. Then Reza Samadi, co-supervisor of the thesis. David Brown, who works at the Department of Physics and University of Norwich. And senior research scientist at McKinsey Institute. Okay. And I am Marie-Christine Angonin, professor at the Sorbonne University. So we will present your work on detecting false positives in this plateau, work done at LISIA, then LIRA at the Paris Observatory. And after, we will ask you some questions. Okay, so let's go.
Thank you very much. I am very happy to present my results of the PhD. I'm also very happy to see the great turnout here. So I will present the work I've been doing in my PhD, half of it in here in the Paris or Meudon, and the other half in Göttingen in the Max Planck Institute. My work is about detecting false positives for the Plato space mission. Now, I will start this talk by giving you some context, trying to convince you why it's very interesting to study exoplanets. Then I will introduce the Plato mission itself. Then I will talk about what we call nominal onboard photometry. Then I will introduce a very known, that we call traditional method for detecting false positives, which is called the centroid method or centroid shift method. Then I will introduce the innovative idea of my work, which is double aperture photometry to detect false positives. I will then hit you with the methodology and how we computed the efficiency for these metrics and these methods. Then I will show the results. And then finally, I will end with my conclusions and some perspectives. Now, why is it very super interesting to study exoplanets? Well, we have very fundamental science questions that go from very basic ideas to, for instance, how common are planets like the Earth in the galaxy, for instance. We also have, so far, up to this morning, we have detected almost more or less 5,000 exoplanets. But of course, it seems that some planets, in terms of size, distance to the star, and other parameters, are more common than other ones. So a good question is if we can infer why some planets are more common than other ones. And of course, exoplanets are also about planet formation. Where do planets form? If they change their position at some point, or if they stay there forever. And of course, now it's a very big theme, looking for atmospheric characterization with the idea of looking for biosignatures to think about life in other planets. Now, Plato, well, so far we have the experience of a lot of, not a lot, but some space missions and ground observations as well. For instance, we have Koho and Kepler and K2 and TESS that revolutionized the idea of the census of exoplanets, detecting a lot of exoplanets with high precision photometry. But also we have other missions like Cheops and the James Webb Space Telescope that focus more on the follow-up of atmospheric characterization. In the near future, we will have another mission called Ariel, which will also follow this path of atmospheric characterization. So now, with this experience taking into account, I will introduce you the Plato mission with this nice plot here. Here we have detection plot. We have the stellar mass of the host star on the y-axis, and the semi-major axis in AU in the x-axis, and we have here a very rough estimate of the habitable zone. So as you can see, this detection plot shows that not a lot of Earth-like planets are known in the habitable zone of their host stars. This plot shows discoveries from the missions I showed you, Kepler, K2, K-OPS, etc. But on this slide, I show as this blue shaded region, the domain that Plato will target. We have less planets here because these are the characterized planets, not the detected ones. So as you can see, there is no characterized Earth-like planets in the habitable zone of solar-like stars so far. So this is exactly what Plato will look at. In principle, Plato will populate this plot a lot in this blue shaded region here. And this is very important because it will solve some of the questions I presented to you in the first slides. Now, Plato is a very super cool mission. It has primarily two scientific goals. One, like we can think in Plato like a mission that has exoplanet interest, but also seismic interest. So one of the main goals is to detect a large number of exoplanets, especially Earth-sized planets, in the habitable zone of solar-like stars. But also Plato would like to investigate seismic oscillations of the host stars, getting by this the age of the stars. So, but also within the Plato mission, within the Plato program, we also have envisaged on-ground radial velocity follow-up, which also makes Plato very special because it's a mission that contains the ground-based follow-up as well. So in principle, Plato will use transits to obtain the orbital inclination and the transit depth, plus seismological like characterizations or measurements, providing radius of the star, mass, and age. And we'll use a ground-based radial velocity to obtain the planetary mass to completely characterize the systems. Now, it is very important, the thing that I will mention is that Plato will focus on bright stars. These techniques, especially seismology and radial velocity, need bright stars in order to be performed. And transits, to some extent, they also need bright stars. And this is very important because, for instance, Corot and Kepler didn't manage to get the seismic measurements because the targets were just too faint. And for this, the test focused on bright stars, but they also never managed to get some seismic observations because of the duration of the observation, which is very small. Now, here are some science goals connected to exoplanets from Plato. As I mentioned, Plato will help to study the evolution of the planetary systems with age, the architecture of the whole thing. Also, if there is a correlation between that and the stellar parameters of the host stars, of course, he will identify good targets for spectroscopic follow-up of the atmospheres. And of course, and this is very important, we'll analyze the dependence of the frequency of terrestrial planets in the environment they form. Now, more specifically, for an Earth-like planet orbiting a solar-like star, which is a G0 dwarf of magnitude 11, we want these accuracies. For precision, we want 5% accuracy for the radius, 10% for the mass, and also 10% for the age. Now, how will Plato reach its goals? Well, there are a lot of answers to that question. First of all, we need a huge field of view because we want to observe as many bright stars as possible. We know that there are not that many bright G-type stars, so we want to observe as many as possible. In order to do that, we need to have a large field of view. And also, we know that an Earth-sized planet at 1 AU from a star like the Sun would have a transit depth of 84 ppm. And that transit lasts 13 hours. So this is very important because it drives one of Plato's most important photometric constraints, which is we need to have a photometric accuracy of at least 50 ppm in 1 hour in order to detect an Earth-like planet around the Sun-like star at 1 AU. Now, furthermore, we know that in principle, an Earth-like planet around the Sun-like star should have an orbital period of 1 year. So we know that in transit detection, the magic number is 3. We want to have at least 3 transits to say that we, with confidence, or with some confidence, we detect a planet. But if we can have 2 transits, it will also be good. So this implies that Plato will need to have very long and very high precision measurements of monitoring of the same stars for more than 2 years. With all this into account, I can introduce you the Plato payload with this very nice figure here. Now, Plato, here are some key points. Plato is expected to be launched in the late 2026, maybe on Christmas, maybe not. And it will orbit around the second Lagrangian point in the Earth and Sun system. This is a very good place to be because it allows you to have these continuous and precision measurements of monitoring of these same stars. And as I said, Plato will focus on bright stars, mainly to allow this ground-based RB follow-up. And the mission lifetime of Plato is of 4 years. We all expect to be extended to 8 years, this extended lifetime. And also Plato has a multi-camera approach. It is a telescope based on 26 telescopes. 24 of them are called the normal cameras, which are used for the main science and photometric measurements. And 2 of them are called fast cameras that are used for fine guidance, but also for the photometry in the red and the blue. Now, I can introduce you now the Plato cameras. This is a representation of it in the right. Each Plato camera has a cadence of 25 seconds because the CCDs of Plato have an exposure time of 21 seconds and a readout of 4 seconds. So that's how the 25-second comes into account. And false cameras have a cadence of 2.5 seconds. And as I said, they will observe the brightest Plato targets and they will be used for fine guidance. And now in the field of view, in the focal plane of every Plato camera, we will have 4 CCDs. Here is a photograph of a real camera with the 4 CCDs in the focal plane. This picture was taken in MSSL in England. And these are the 4 CCDs here. Now, there's a direct link to the amount of information Plato will process. As I show you, each Plato CCD has around 20 million pixels. Therefore, each Plato camera has 4 times that, so 81 million pixels. So for the total 24 normal cameras, we're talking about more or less 2 billion pixels for the 24 cameras. On top of that, we have a telemetry constraint, which is very hard, of 435 gigabits per day. Of course, this constraint does not allow us to download full images for each target, like happens with this. And also doesn't allow us to download small images for every target, like people did for Kepler. In Kepler jargon, these are called post stamps. But we cannot do that because we have a very big telemetry constraint. Furthermore, at a normal cadence of 25 seconds, we can download only 29,000 images for a single camera. So all this creates the necessity to have a lot of measurements performed on board, simply because we cannot download the information of each target and then extract the photometry or create the light curves on ground. So a bunch of those have to be on board. Now, in order to reach these goals and taking into account all these constraints, all Plato targets are divided into 4 samples. or 4 stellar samples called P1, P2, P4, and P5. For the majority of the Plato targets or the Plato samples, the photometry will be extracted on ground because they are the brightest ones. But for the largest sample, which is the P5 sample, we will have to compute the photometry on board. The measurements have to be obtained on board, and that is why my thesis is focused on the P5 sample. Now, as a matter of fact, if we look at the P5 sample in detail, we will see that for the 9,000 brightest targets of the P5, we will have what we call images downloaded on ground in order to extract the photometry on ground and not on board. Now I can introduce you the concept of the images. So all photometric measurements of Plato rely on the concept of an image. An image is a fraction of a CCD. It's a 6x6 CCD square. This has been shown to be enough to encompass almost all the flux of a given target. For very saturated stars, we might have larger images, but the typical ones are just 6x6. And they were going to be used for both on-ground and on-board photometric extraction procedures. For the on-ground photometry, we have a very powerful method called PSF fitting. And for the on-board photometry, we have aperture photometry. We have to use aperture masks to obtain the light curves. Yeah, so now I will focus on aperture photometry now. And the name of the game for aperture photometry in Plato is binary masks. In a very interesting paper, Victor Marchiori showed that binary masks are actually the most or the best option to use for Plato onboard photometry. They are actually better than what we know as the weighted masks because they are the best. They offer the best compromise, the best trade-off between the noise and a sensitivity of the background flux sources. So in this image here on the left, we have an image, a 6x6. We have a target in the middle, and around the target, we have a nominal mask, which is just the pixels that are going to be used to extract the photometry of the target. Now that I have this figure here, it's important to tell you that each Plato pixel is of the size of around 18 micrometers, and this has on the sky a size of 50 arc seconds. This is interesting when you take into account other missions pixel size for other type of measurements. So now, here is a very big equation called the NSR, or the noise to signal ratio. The noise to signal ratio is actually the key performance for Plato photometric measurements, because this formula here, this equation here, gives you an idea of how to build binary masks, or as we call nominal masks. Now, this expression has all the noise sources in a given image. We have the noise coming from a target, from the contaminants that would be present, and also for the detector and quantization noise. And of course, since transits last typically several hours, we would like to scale this NSR here during 1 hour. This scaling factor here takes into account the number of cameras, and it's in ppm. And also, I mean, here we have what we call the mask, these omegas, and all these n indices that run here are, this indicates that it's running on the 36 pixels of a given image. So with that into account, with that in mind, we can define something that we call the aggregate noise to signal ratio. The full procedure to go from the previous slide to a binary mask is detailed in this paper by Marchiori. It's a long procedure, so I won't put it here. But this is very useful because it gives you the size of a given binary mask. For instance, here we have that the mask should be 5 pixels in size. And this formula gives you not only the size, but the specific pixels in a given image that will be used for the mask. In this case, they are these 5 pixels. Now, this is something that is very important. This is a depiction of a true positive. That means a planet transiting the target star and is captured by the nominal mass. This planet here has a transit depth of 400 ppm. It actually corresponds to cobalt 7b. So it's a famous example. And this is what a light curve will look if we use a nominal mask to catch it. And this is what we call a true positive, of course. But now the more interesting stuff, or more interesting to my work, is the next one, which is a false positive. If we have here again a target with a nominal mask around it, but now we have a very mean contaminant close to the mask. And if this contaminant has a magnitude of 14, for instance, have very big transit depth, for instance, 80,000 ppm, what will be caught by nominal mask is a light curve that looks very similar to a true planetary transit, to the true planet that I showed you before. So this is very important because for Plato, eclipsing binaries that are very close by to the nominal mass in a given imagejet can create false positive, can create transit light curves that look planetary, but they are not planetary. And this is exactly where my thesis is focused on, detecting false positive primarily caused by eclipsing binaries. In my thesis, I address this problem for the onboard photometry Plato procedure. I develop a method to detect such false positives, taking into account Plato constraints and CPU limitations and memory limitations as well. And we proposed this innovative photometric method called double aperture photometry, and we compared it to a traditional one to detect false positive, which is the central shift method. Now, in a given real case scenario, we will have an imagejet here with a target, a nominal mass, and a bunch of contaminants present there. We could have up to 100 contaminants. Here we have only 6 to show you how it looks like. But this is useful because I can introduce the concept of total flux, which is just the total flux contributions in a given imagejet. This is the flux of the target plus the sum of all the individual fluxes of all the contaminants. Now, this is also interesting. I can give you some definitions here, which is called the stellar individual, the stellar pollution ratio, and the total stellar pollution ratio. Now, if we want to know the individual contribution to the flux measurements in a given imagejet, we will just take the flux of a given contaminant and divide it into the total flux to create this individual stellar pollution ratio. Now, for the total contribution of all the contaminants, we will call the total SPR. And this is just the summation of all the individual stellar pollution ratios. And this is also very useful because you can define the observed transit depth, which is not the real transit depth, which is delta B, but the one that is diluted by the contamination represented by the stellar pollution ratio. So this is very useful because we can have all the information from these contaminants. And now I can introduce the concept of statistical significances. Yeah, whenever a transit happens, for instance, in an eclipsing binary, a signal has to be detectable in the nominal mask. And in order to do that, we have to define what we call the statistical significance. That in this case is just the observed transit depth of a given eclipsing binary over the noise. The observed transit depth is the one I defined you before. And the noise is just the NFR over 1 hour divided by the transit duration and the number of transits. And then a signal becomes detectable whenever is above a given threshold that we call era min. Now, then a false positive can occur whenever there is a transit from a contaminant and creates a signal that is significant enough. That is represented by this. The significance of eclipse binary is higher than the given threshold, eta min. And we can say that this threshold value, eta min, it's of 7.1. This is a very nice value. It was adopted for Kepler in this paper by Jenkins. Jenkins proposed this value of 7.1 to ensure that only one false positive will occur for the whole Kepler mission lifetime due to statistical fluctuations. But some authors have proposed other numbers. We have papers with eta min of 3 or 10. So we can vary a bit the value of eta min. And now that I introduced that, all those definitions, I can present what we call the traditional method for deducting false positives, which is the centroid shift method. Now, this method comes from Kepler times. As a matter of fact, the first paper using centroid shifts to compute or infer the existence of eclipse binaries in the images is from Natalie Batala from 2010. And then it has been used a lot in Kepler data, for instance, from rrez and also by Hedge in tests. So the idea of a centroid is just the center of light or center of blackness of a given aperture. And the center in the x direction is represented by this expression here that takes into account the mask and a given coordinate. Of course, the expression for the y direction centroid is analogous. And also, what we care about is the periodic variation of the centroid shift with time. For instance, if we look at the figure on the left, we will have a target star. It could have a transit of a planet or not. And then we have a binary eclipse an eclipse in binary on the left. And the X, on the right, and the X mark shows the position of a given centroid, the center of right or center of brightness. And whenever there is a transit happening in eclipse in binary, and the companion goes back, there will be a shift in the position of the centroid. And actually, if you can resolve the system, both targets and eclipse binaries, the direction of the shift gives you the origin of the transit. So then when the companion comes back again and shows itself, the shift will go back to the original position. So if we are able to measure this periodic shift in the position of the centroids, we can actually detect and infer the existence of a false positive. There's a very good paper from Bison that shows a very deep centroid shift. Here we have these red and blue measurements. The red measurements refer to right ascension coordinates, and the blue one are declinations. And these are out of in transit, and these are out of transits. So whenever there's a transit, you see a shift in the measurements of the position. So now, the centroid shift of each direction is just computed as the out of transit minus the in transit measurements for both directions, x and y. And then what we call the absolute centroid shift is just the quadratic sum of both the centroid shifts in x and y. It's using the Pythagorean theorem. And this allows me to introduce something that is important because it's present on a paper I wrote, and it's on revision now, which has a bunch of equations. And this is the idea that centroid shifts can be defined in terms of transit depth. In the paper, we found that any transit centroid shift can be expressed as the multiplication of this lambda factor and this gamma factor. The lambda factor is actually proportional to the transit depth, showing this that the transit depth is a driven entity or the driven term for centroid shifts. And the gamma factor is, it takes into account the position of centroid in a given direction, and also the position of the coordinates. And it takes into account the flux of a given contaminant, the contaminant that is creating the shift, or the contaminant that is having the transits. And just as we did for the flux, I can define a threshold to know whenever a transit signal, a centroid signal coming from a transit is detectable enough. So we have a threshold that we call eta delta z min, and we can define the significance of a given threshold That is just the magnitude of the centroid divided over the noise. Here I have a little expression for the noise in the x direction. It is very similar to the one for the y direction, only in analogous fashion. And this is also very important because this allows us to have a direct measurement of centroid shifts and centroid shift significance. Now that I introduced you this traditional method for detecting false positives, I will talk about the idea we proposed in this thesis, or I proposed. So the idea is what we call double aperture photometry. This is based on having two apertures or two masks in a given image, not only the nominal one, but an extra one. This extra mask has the purpose of investigating the contaminants that could be eclipsing binaries and that could, for instance, create false positives. The first time this idea was proposed was in scientific discussions by Alexander Santer, Pascal Witterman, and Victor Mercury, but they never computed the efficiencies of double aperture photometry. They never computed also, or they never defined double aperture photometry in a rigorous way. And this is exactly what I've done. So yeah, there are two options for double aperture photometry. This extra mask could be either a secondary mask, or what we call a secondary mask, or an extended mask. Now, secondary masks are typically smaller binary masks than the nominal ones. They are obtained using the same procedure I showed you for nominal masks. The only difference is that we are centered on the contaminant star and not in the target. So contaminants are usually fainter. That's why secondary masks are usually smaller. And of course, the secondary masks are centered only in one contaminant. Actually, in the contaminant with the highest SPRK value, being that contaminant the most problematic one, the most probable to cause a false positive. Now, in comparison, so in change, extended masks are way bigger than standard masks. The way to build extended mask is typically by taking the nominal mask, which is depicted here with these black lines, and surround the nominal mask by a ring of pixels. Typically, this ring of pixels is of just 1 pixel, but if you want, you can have 2 pixels or more. And since they are way bigger, they can reach more contaminants. And of course, that makes them a little bit more sensitive to the pollution present in a given image. Now, I will show you a little example of how double aperture photometry is useful for detecting false positives. We'll have an example case here where you have an image. We have a target. In this case, it's a target of magnitude 11. We have a binary mask or nominal mask here of 5 pixels. And we'll have a contaminant star of magnitude 13, very close to the nominal mask, having transits this deep. Now, if that is the scenario, if that is the case, and we use an extended mask, and of course, if the transits are happening in the contaminant, we will have 2 light curves, because of course, if we use double aperture photometry, we will have 2 light curves per image, one from the nominal mask and the other one from either the extended or the secondary. So in this light curve here, the transits happening in the contaminant caused this dip in the nominal photometry that might look like a planetary transit in the target, but in the extended mask, we will have a way deeper transit. So by this direct comparison, by just looking at the light curves, we can see that the origin of the transit is not the target, but a contaminant, because it's just bigger. In the same way, for a secondary mask, we see something even more deep, because the secondary masks are smaller, the noise is smaller, so we have a very deep transit depth, or a very big transit. So this is awesome, this is very nice, because you can see clearly that the method works by direct comparison to the false positive. And now what I did is that I compare the overall efficiency of double aperture photometry and centered shifts. Of course, with the idea that we don't have to pick one or the other one. At some point we can play, we can have both, but it is very, very interesting to see which method is more efficient. So in order to compute the efficiency, for instance, for a double aperture photometry, we just follow a very simple approach. We compute the ratio of all the false positives the nominal mask is sensitive to, like the total number of false positives. And then we ask how many of those guys we can catch. And that's the number of false positives detected by, in this case, extended mask. But for the secondary mask, it's none. And that's just the idea, how many of the total ones we can catch. And the expression for the numerator of how many false positives the extended mask can catch is based on three conditions. The first condition is that the transit depth in extended mask has to be significantly detectable or significantly deeper. The second condition says that the transit has to be detectable in the extended mask itself. And of course, the third condition is that the transit has to be detectable in the nominal mask. Because if it's not detectable in the nominal mask, then we don't worry about it at all. And of course, these are all these conditions are performed for every contaminant in every target. The summations are not here, but they are implied. And in the denominator, we have the expression for the total number of false positives the extended mask is sensitive to. So we just count how many contaminants can overpass a given threshold. And this expression here, this sigma delta, is just the quadratic sum of the errors or the noises of the transit depth in each mask. Now, in a similar way, I compute the efficiency for centered shifts. In this case, for the centered shift using nominal mask, and the approach is the same. We counted how many false positives we can catch using nominal centroids out of the total number of false positives nominal mask is sensitive to. And there is a little bit difference between centroids and fluxes because for the numerator expression, we only took into account two conditions, not three, like for the flux, but only two. The first condition is about the transit creates a significant centroid shift. The shift is detectable. And also, the condition is the same as the last one in the extended mask, is that the transit has to be detectable in the nominal mask, because if it's not detectable, and then the denominator is the same. It's the same that for the flux. It's the total number of false positives. So we just proceed, and we follow this methodology. We obtain a huge catalog of stars from Gaia Data Release 3 of around 100,000 stars. And this is to represent the field of view of a single Playboy camera. And we took as targets all of the stars, or a fraction of a lot of stars in the P5 magnitude range, which is from 8 to 13. And we took as contaminant stars all the remaining. So we had a lot of contaminants. And of course, since PSFs are important in our analysis, we use a catalog of around 4,000 Plato representative PSFs, the latest in the market for the computations. And for every target, we compute the nominal mask following the Mercury approach. And maybe I have to say it now, but this has to be done for each target. So maybe we can have a different mask for each target. There is some degeneration. Some targets have the same mask. So we compute it for each target. And then, and this is a very important assumption, we assume that every contaminant is in a blended eclipse binary. So like a worst case scenario where everyone are eclipse binaries. And all of them have the same transit depth, 85,000 ppm, and the same duration of 4 hours. These values are actually the median values from this very useful resource here, which is the Kepler eclipse binary catalog. And then we computed the efficiency for both double aperture photometry and centric shifts. And these are some of our first results. We obtained an occurrence of false positives for the targets in the P5 sample, given all the assumptions I showed you. So these are good news because for around 43% of our targets of our catalog, we will have no false positives or 0 false positives. For around 33% of the targets, we will have only 1 false positive. And for all the remaining targets, we will have 2 or more false positives. This is very nice and very important, but this is, of course, restricted to the assumptions we did or we took into account. Then I can show you some plots for the efficiency of the Walla particle topology. On purple, we have the secondary mask, and blue, we have the extended mask. This is plotted for a given region of the magnitude of the Plato P magnitude system for a given region of targets. And we see that secondary masks have a very good efficiency of pretty much like 90%, 92%. And extended masks have an efficiency of around 70%. Which is very good, very interesting. But then we computed the efficiency for centroid shifts. And we realized that the centroid shifts are way more efficient. Or no way, but more efficient. In these plots here, I show the efficiency of both the nominal centroid and extended centroid shifts. Here is a little zoomed-in window that shows that nominal centroids have a very, very big efficiency of around 98%. And extended centroids have an efficiency that is comparable, but a little bit less. It's a little less efficient. Now, with all these results into account, we can show an example of how we assign the metrics for Plato. For doing this, given the results, we also need to take into account some telemetry and CPU constraints. These are actual numbers about the resources we have to assign, where we have and we are available to assign. For instance, these are given per camera. We have only 7,000 or 7,400 nominal centroids as well as extended centroids. We have a bit more for extended or secondary fluxes. That means how many extended or secondary masks we can have. And we have more for the nominal fluxes. Now, what we did is to create this little table here that I will explain a bit. So we have a given scenario where we have 0 contaminants in an imagejet able to create a false positive. What we propose is to use an extended mask. We would have 1 contaminant able to create a false positive in an imagejet. We propose to use either a nominal centroid or a secondary mask. And if we have 2 or more contaminants able to create a false positive in an imagejet, then we would have to choose between extended mask or nominal centroids. This is very important because in the Plato pipeline, the assignment of the metrics is done on a per target basis. We check for each target which metric should we use. And yeah, this is some explanations. If there are no contaminants, then we choose an extended mask by default, if the resources allow it, if the previous slide numbers allow it. And this is because we can use extended mask as a safe option. Like if we miss 1 contaminant or we don't have enough information on the immediate contamination, then extended flux is a safe option. And on the other hand, if there is only 1 contaminant that is a false positive, we can use a secondary mask because, as you saw, secondary masks have like an efficiency of 90% in detection. So it only monitors 1 contaminant at a time. So we can use the secondary mask there. And for the remaining 10% of false positive that a secondary mask can lose, for those, then we can use a nominal centroid since they are so efficient. And then for the case of 2 or more, we directly count how many false positives either the nominal mask or the extended flux can detect. Now it's time for conclusions. As you saw, nominal centroids can detect around 98% of false positives. So they can be used, given their huge efficiency, They can be used alongside whenever whenever another metric is not significant enough. For instance, secondary mask. Then extended centroids, since they have a little less efficiency, they could also be used, but it turns out I did some computations and I realized that the number of false positives detected by extended centroids, but not by nominal centroids, is only less than 1%. So there is therefore less or a marginal interest for extended centroids just because nominal do well. And then when it comes to flux, we have secondary masks that reach 90%. These can be used for most images, since they can monitor only one contaminant at a time. And then we have extended masks. And as I said, these can be used for images with no contaminants, but also with no contaminants, able to create a false positive. But also for images where 2 or more contaminants are dangerous. And also, I proposed a strategy for Play-Doh to maximize the number of detected false positives, optimizing the number of resources available. And now I can say something about perspectives of this work. I started to investigate the use of a distribution of transient depth and durations for the overall computation. Not anymore assuming that all contaminants have the same transient depth and all contaminants have the same transient duration, but using a distribution instead. I started to crunch some numbers on that. And also, these results could be useful for future space missions. I think, for instance, in this NASA mission, the Nancy Grace Roman Space Telescope, that is expected to be launched the year after Plato, and also the HWO, the Habitable Worlds Observatory, which is, oh, there's a typo, it's 2014. It's not that far. And also, some important perspectives is the idea of a differential analysis. This comes into account this comes to discussion if we remember the first condition of the numerator of extended mask, that we said that the transit depth has to be significantly deeper. And this comes from the fact that if we take not both extended and nominal light curves independently, but if we take the difference of them, for instance, by either subtracting the extended mask from the nominal mask, we will have, of course, a smaller transit depth, but the sigma delta, which is the noise of extended and nominal transit depths, will be smaller. Then the first condition of extended flux will be relaxed, and the extended mask will be more sensitive to the detection of false positives. The idea is just to reduce the value of the noise in the light curves. And we can do that by simply subtracting them. And also, this is some interesting point. I told you that the on-ground method for the on-ground method for photometric extraction for Play-Doh, it's called PSF fitting, which is a very powerful method, but very computationally demanding. But it turns out that the PSF fitting could also, in principle, be used to detect false positives. So a very interesting idea is to see, hey, what if we start doing PSF fitting to detect false positives? Since with this method we can disentangle the contaminant contributions here, the target contributions here, and see how it goes. Like maybe we can even compare PSF fitting to double aperture photometry to see which one is better, and maybe use the knowledge we had from double aperture photometry to try to see if PSF fitting is also useful for detecting false positives. Because PSF fitting has very important advantages. The main one is that you can disentangle the contribution for the target and contaminants. But of course, if the target and a contaminant are very close, then it's very difficult to disentangle. It will be interesting to know to which extent PSF fitting is useful for detecting false positives, which I think hasn't been done. I don't know. Yeah, that's all. Thank you very much for your attention.
you very much for your presentation. Do you want to drink?
No, I'm okay with it.
You're okay. So we can go on the questions.
Yes, yes.
Okay. So I will ask first the referee to ask questions and comments.
Yeah.
And especially Nadej, are you ready to speak?
Yes, I am.
Okay.
Okay. Thank you. Thank you very much. Can you hear me well?
Yes.
Okay. First of all, I would like to apologize for not being there in person due to some teaching constraint this afternoon. So I thank you for your very clear presentation, and I do have a few questions on different aspects. So I will start with the assumption that you took about the EB's properties
Yes.
in your work, and I have a couple of questions on that.
Yeah.
I have two questions. The first one is, how is the distribution of the properties of the EBs? Because you took the medium, but in practice, I suppose there is a large distribution. How would this impact what you have done? And the second question is, since you assume that all the background stars were possible contaminants, the percentage that you obtained, for example, in your slide 40 here, that one, they correspond to the fact that you took, you consider all stars as contaminants, but if you were to consider the actual occurrence rate of EBs, what would be the percentages in that kind of figure?
Yeah, okay. First, the distribution of parameters here of fixed transit depth and duration I remember from this table, it's not very skewed, it's like a very Gaussian distribution. So I took the median value there, and I think, because the idea is to randomly select values from this distribution and use them in the efficiency computation. So I think the results will change a bit, but I don't know. It's still in the ongoing work. And now with this other question, since here I'm assuming that all eclipse in since I am assuming that all contaminants are eclipse in binaries, then if we took a realistic case, I think there will be even less false positives for Plato targets, because we have very bright stars. Since Plato observes bright stars, the amount of contamination is less, for instance, than for Kepler or Cole. So in principle, if we take a realistic approach of the expected contaminants, then we will be having less false positives.
Okay, but you have not quantified the difference that it would lead to.
Yeah, no, not yet, but
Okay. I have another question about the use of the large catalog of Paris-PSL that you've been using. So what do they where does that large amount of PSF come from, and are they representative of all the situations that will be met when observing in a couple of years? How do you how do that impact what you've been doing?
This I didn't mention, but these PSFs come from Thierry Apochou at DIS at the test house. So they've been using a real Plato camera to produce these PSFs, and a different field of view positions. I think 44 field of view positions. So what we do is just taking the closest PSF to give it to each target in the field of view, and then compute the nominal mass. That's why the PSF is more important for the nominal computation, nominal mass computation.
So that's about the field of view, but I suppose there are other parameters. So how did you select them, and did you take them randomly or?
Yeah, I remember there were some parameters about like the width of the PSF and the temperature of the source star. I think it was 6,000 Kelvin. And I did some computations in the thesis for different PSF shapes, different PSF temperature sources. And yeah, it doesn't change that much.
Okay. I have a question about the on slide 16, because I did not understand why in your formula of the noise to signal ratio you don't have the at the numerator you don't have the noise, you have the flux, the ITN, and well also IKN. Why is it not the noise there as in the paper by Marchiori?
Yeah, I mean, in this is since the photon noise follows a Poisson distribution, the variance is the mean of the. I mean, the variance of the flux will be the mean, so we can just directly put here
Okay,
the
so
value. But yeah, I didn't mention, but yeah, this should be a sigma of the photon noise. But since it's a Poisson distribution, it's the same. Also for the contaminants.
okay. I have a question about the results of the proposed strategy. I was a bit frustrated by the fact that in the end, you did not really quantify the strategy that you proposed. You have estimated the efficiency for each method separately, but then when you propose a strategy, it's not quantified in terms of making a simulation of in the end, how many would be with that method, how many with the other method, and in the end, what would be the um, uh, resulting efficiency. Have you estimated that or started to do that?
Do you mean this table here, the strategy here, or?
Yes, starting from this, you did not uh, derive an efficiency of that proposition.
Yeah, since this is done for a per target basis, like for each target individually. Yeah, I haven't done that. I mean, this is based on this overall efficiency I showed. But yeah, maybe we'll.
My point is that you have a general rule that you wish to apply, but in the end, you still have the constraint of maximum number of computation you can make for each of the approaches. So in the end, you could simulate what it would give given those constraint and given this strategy for your field of view, not as a per target basis, but to go to the next step. How would this be implemented, and what would be the efficiency?
Yeah, no, I mean, I don't know. I haven't done it. It's a good one.
I have a very general question about, it's really about the context and something that you mentioned at the in your chapter 2. When you describe the Plato objectives, you say that stellar properties could have a huge impact on in planetary habitability. It's really a context question. Could you say more about this? And also, could you say how stellar variability would that impact what you've been doing or not?
Yes, it was here maybe. I'll put it here. Yes, I mean, so far we haven't. First, the stellar variability. I know it can impact, for instance, with the evolution of the habitable zone, for instance. the distance of the habitable zone to the star could change with time if the variability also changes. And I think so far we haven't taken into account the stellar variability in our computations or stellar activity, but I think given the difference in the time scales, we could represent the stellar variability or stellar activity as an additional source of noise, for instance, in the NSR expression.
Okay. I think I will ask a last question about the future. Could you say a bit more about the differential approach where the noise is not independent? Do you expect, what kind of impact on your result do you expect?
Yeah, I expect to have a larger efficiency for the extended mask. The efficiency will go up because the first condition in the numerator of the efficiency computation is more relaxed. So we expect that direct increase in the efficiency. Yeah, I mean, by taking this approach, since we are taking into account the difference of the light curves, we will have smaller transit depths, but also the noise is smaller, so the efficiency will go up.
Okay, well, I think I will stop here for the questions. Thank you.
Thank you.
Thank you very much, Nadej. Then I ask Magali if you would choose.
So thank you, Fernando, for your presentation. I think I wish to emphasize the fact that the study you have done for your PhD is very important for the mission. And so it's good to see you have kind of quantified the use of this original photometric approach. So I have also a couple of questions. Maybe the first one, I think it's, you can remain on this slide or move to the next one. I mean, you talk about the secondary mask, and I was a bit first. I have two questions, in fact. One is, how will you choose the most relevant contaminant on which put a mask on it? That's my first question. Because when you have a series of contaminating stars, which one will you pick among them?
Yeah, I think the idea is to pick the one with the highest SPR, the one who has the biggest contribution, because the individual stellar pollution ratio is the flux contribution of a given contaminant. So the contaminant with the biggest contribution then should be the one we will be focusing on.
Okay. And yes, in your manuscript, you speak about the centroid shift in the secondary mask, and I didn't understand that, because if you have just this teeny mask dedicated to this star, and the signal, the binary, the contaminating star is a binary, so you will not have any shift.
Yeah, especially if we have a secondary mask of 1 pixel.
Yes.
There's like this, there is zero shift. Yeah, that is something we have to put a condition there. Like if secondary mask is 1 pixel, very small, then the central shift is basically zero. There's nothing.
There is nothing to look at. I mean, no. Because you don't expect any. I mean, you have the proof, but just by the photometry, more or less, that the signal is occurring on the contaminating star.
Yes, but and also, I mean, in the thesis I show that secondary centroids are way less efficient than the other ones.
I don't really understand how they are calculated. Okay, so more or less related. Okay, you choose a kind of an extreme
approach
bed I mean, binary equation binary, okay, because the transit depth is pretty important, but I think you have the material, it's more or less all hidden, but did you check the dependencies with the magnitude difference between the contaminant and the star, and also the distance between the two?
Yeah, I mean, I have the information in the sense that I have a distribution of distances in pixels from each contaminant to each target, and also the magnitude difference between each contaminant and each target. So I have it, but I didn't explore it yet. But I for sure have the information.
I think that would be something very essential for us, because it could answer Nadej's question, and you should proceed because you have everything. Even if it's you don't make the depth of the binary changing, at least you can assess the effect on the magnitude difference in distance. Yes, and I wonder if your target has no contaminant. So what's the point in having an extended mask? It's related to your slide 44.
Yeah. Yeah, this comes from a conservative idea. Like maybe there are flow sources that we didn't manage to know beforehand. So we can use an extended mask as a safe option. Just in the case we don't know all the information about the contaminants, it could be an emergency.
That's okay, I can get it, but in the same time, maybe for us, the contaminant that will be the most trickier are those which are very nearby to the targets. So in that case, well, maybe the extended mask is not that relevant.
Yes. And it's only if the resources allow it. They will have a priority level of 0 in the assignment of the matrix. And
in that case, why not keeping that for the case where you know you have a contaminant?
You can use it for the case of having 2 or more contaminants. But if we have only 1 contaminant, then the secondary mask should be enough.
Well, we need to see numbers, in fact. Okay. Maybe a last question, which is related to the comparison of the difference between the extended flux and the nominal flux. You suggest, because you said that no, at the end in the
yeah, here
it doesn't matter. So when you suggest to make the difference between the extended flux and the nominal flux, let's call it this way. Yeah. I mean, here it looks to me that if you do the deep, well, you said that the depth will be smaller when you take just the extended minus the nominal, but then at the same time, the signal of the bulb will be, well, maybe not, in fact, I would say less diluted, but might not be correct, in fact. It will be clear in the secondary mask, but not in the extended one, in fact. Okay, so because I'm also thinking of how we can use it for the routine machinery, it's yes, okay. I have to take a look.
Yeah.
Yes. Okay. Okay. Thank you very much.
Thank you, madam.
Follow up on a couple of Magali's questions.
Yes.
If you have 2 contaminants that have the same SPRK, how do you pick which one you target for secondary mask?
We have two stars with the same SPRK. I think the idea is to have an extended mask and a secondary mask. The main problem of the secondary mask is monitors only one star at a time.
And then all your examples, you have, Maggie mentioned contaminants within or very close in, and in all of your examples, all of your contaminants are outside of the normal mask.
In the examples, yeah, but they could be inside.
Okay. So do you have cases where in your full sample where you have a secondary mask that overlaps with the normal mask?
In principle, yes, they could overlap.
Okay.
And I am aware that that shouldn't be a problem in terms of like resources and everything. But yeah, they could overlap.
Does that affect your results in any way, do you think?
No, I don't think so. I mean, there will be pixels in common in both masks for the definition of the letters.
You had the efficiency at a function of magnitude.
Yeah.
Yeah, it's this one. Why does the secondary mask drop?
At 11,
At 11, yeah.
is the famous Plato 11 magnitude.
Yeah. So do you have more stars in the sample of that particular region? Is there something about that magnitude?
That's a very good question, and I don't know actually. Because it looks significant, like 3 sigma.
Yeah, it's quite a good drop.
Yeah. What's a good question?
Because in your thesis, when you started looking at the field of view distribution as well, there were some other odd effects where, as you moved outwards in the field of view, you got this strange jump.
Yeah, 11.
Yeah, and then also in position, right?
Yeah.
You split your rings up into different distributions, and
Yeah.
your cell evolution ratio was hard. What this efficiency bump as you moved outwards.
Yeah.
I was wondering if you had any ideas about why that was the case.
No, it's a very good question. I don't know. I mean, as a first sight, it seems random, but I don't know.
Go back to the slide where you had the ideas for future.
Yes. Okay.
And the previous one. Yes. Sorry. Given that the extended masks only detect 70% of false positives, do you think, and you included them in your strategy, but do you think it's worth using them at all if they're only 70% effective?
Yes, I mean, it's worth it. As a matter of fact, the aperture photometry is cheaper in terms of CPU and telemetry budget. Because for centrages, we have to measure 2 coordinates of a given centroid. We download them, and then the centroid chips are completed on ground. But for extended math and secondary math, we have not. Yeah, I think extended math are they can monitor several determinants at a time. That's the best.
When you're comparing, well, not, when you're comparing the efficiency between the metrics that you're considering, a lot of them are very similar. There's some subtle differences with like stellar types and stellar temperatures and things like that. I think that although those are not 3 sigma significant, some of them are 1 sigma significant.
Like this.
Yeah, so some of these are small effects, but how important do you think those small effects are? Do you think the fact that some of them are different at 1 sigma level is important?
I mean, for instance, in terms of stellar type, we didn't consider any correlations with stellar type. We just assume the eclipse binaries and transit depth and durations. I don't think it will change a lot.
Thank you. Now I'm asking the supervisor if they want to tell something or even ask questions. That happens sometimes. So I don't know, Reza or Aaron, if you want to be. Okay.
I wanted to give some context of the work. Probably we don't know initially the goal was to look at some CCD effects. We wanted to model this effect and to correct the data in order to reduce as much as possible the residual error for Plateau. But at the same time, we had this question of extended mass that was said by Fernando. The idea of extended mass comes from discussion we had with Alexandre and Pascal Kuterman and my former student Victor Marcury, and we had this idea. We did some very estimate, and we decided to implement this on board because the development of the onboard software is very time-consuming. It's a long process, so we had to make this decision very early, and we have decided to implement this on board, but we had no idea about how efficient it was this technique, and also how to assign a given target, so a given extended mass, how to compute the extended mass. So we proposed to, because it was urgent to have also for the design of the on-ground software, which is the place where we have to compute the extended mass and to upload them on board. It was urgent to work on this issue, and we proposed Fernando to work on this subject and find this subject very exciting, and so this is why we work on this issue and did the work. And I think it's very important for Plateau to be used to detect as much as possible false positive. And now the problem is that in the consortium we have to advertise about this technique to inform them that it's a very useful technique. So, but the next perspective is to consolidate this work and to communicate among the consortium of both this technique. I take the opportunity of this event to thank Fernando for the work he did. Thank you, Fernando.
No problem.
Do you want to say 2 words?
Just a little bit, yeah. I mean, so first of all, yeah, congratulations to Fernando on the very nice work. I think we're all really looking forward to Plato, and learning more about how to squeeze the most science out of P5. This is really important. So I'm very happy to see this work being done.
Thank you. So now it's my turn. I'm sorry, but I'm not working on this subject at all. So my question, I will ask only one question of curiosity. I'm sorry, I don't know anything about the performance of Plato. If I understood well, you use Gaia observation
Yes.
to know that there are the contaminants near the stars.
The targets.
So for Plato, all the stars that will be observed have been observed previously by Gaia, or there is some field of view difference or magnitude difference?
Yeah, I mean, I'm aware there is this big Plato input catalog, which has all the stars that Plato will observe in the different pointings, and it's based on Gaia.
And Gaia have observed all these stars.
Yeah, I think so. Yeah.
Okay, and you mentioned that at the end of your presentation, the next generation, a Raman telescope or HWO, and it will be the same with this telescope. There, what the type of stars that you will observed have been already observed by Gaia. You will be able to use the same comparison to detect, assume that there is a contamination.
Yeah, I believe that these results will be very useful for future missions, especially in HWO.
Yes.
Because it will focus on Earth-like planets like Plato, and then bright stars.
Yes, the same type of bright stars have been already observed by Gaia. That's no problem.
Yeah.
Okay, no, this was just curiosity. I'm sorry, it's not. Okay. And I have a very stupid question, because I suppose that this is very rare, but we can imagine that we have false negative.
Yeah.
This means that contaminants hide
True
any transit because they look so alike and they're opposed to phase, or I don't know. And do you think that your method can detect some false negative also?
Yeah,
So
I mean,
disentangle between the both.
yeah, that's a hard question because, yeah, I mean, if an algorithm tags everything as a false positive, then it's like useless, right? You will be for sure ruling out true positives as well. But yeah, estimates about the percentage of false negatives in this study a bit difficult to address because now we have to focus on the performance using true planetary transits. But yeah.
But it should work.
Should work, yes.
Yeah, okay. So that was my question.
Yeah.
Thank you for your presentation, very clear, and for your work.
Thank you.
Okay, so if you don't have anything to say more, I think it's time for deliberation.
Okay.
So we have to be alone.